Hello everyone, and welcome to our session, The Race to Win AI, Power, Geopolitics, in the DC Data Center. My name is Jalen Lewis, and I'm the events manager here at Peak, and I'll also be your moderator today. I'm joined by Shaun Walsh, the CMO here at Peak, along with Frank Berry, the founder and analyst for IT Brand Pulse, as they dive into how AI is starting to evolve. So before we get started, I have just a few housekeeping items. Questions will be answered via the Q&A chat following the session, and the webcast is being recorded. It will be made available following the session for you to rewatch or share with your colleagues. This is a monthly series, so be sure to watch out for our May session where we will discuss our new program, Films as a Service. So without further ado, I will now pass it off to Frank Berry to get our session started today.
Hi, everyone. So what I'm going to do is I'm talk about the Gen AI Big Bang, and that's all about AI and the expansion of the data center universe. And the way I'm going to start is, first of all, if you all remember about 2011, we all had to relearn what data centers were all about with the emergence of the cloud, new terminology and new meanings to what data center meant to our work and our day-to-day lives. So we're going to have to do that again with AI. We're going to have to learn a whole new data center terminology and in order to understand what it means to our day-to-day life and to our work life. So let's get started. So I like to start with a 100,000-foot view of a situation, but in this case, since we have a universal theme, I'm going to look at a couple light year view of the generative AI solar system. And it starts with users. And it needs billions of them in order for us to be talking about the power that's needed to support this environment. And users are, excuse me, and what the users are using is a complete refresh of the entire universe of applications, consumer, horizontal business apps, vertical business apps, and a whole new class of applications called agents. And I expect there'll be 30 billion of them by 2030. And those apps and agents, they're inextricably tied to models. So you can't have apps and agents without models, and they work together. The apps and the agents are built on models, and those models run in data centers, those data centers that are full of millions of NVIDIA chips. And of course, that's why we're here today, because they require a whole lot of power. So another set of terms that you will need to be familiar with if you want to understand AI is training and inference. And they're two sides of the same coin. So a model like ChatGPT has to be trained. It's scraped the entire universe of the internet universe of all its data. It combines that with a context engine so that it can reason and respond like a human being. And then once it's running, when you're conversing with it, that's inference. So both of them are being done on a model. From a power perspective, over the lifetime of a model, about 10 or 20% of that power is used for training. And this is an important fact because most of the data and charts that I see out on the internet are all about training. But in fact, most of the power is going to be used over the lifetime by people using the model, which is an inference operation. Now, one other thing about this data point is that this assumes a mature market. So I'm going to show you some data later in this presentation where the percent power usage by inference is much lower, and that's because there is not a lot of agents on the market yet. But as the market matures, the power usage is going to look like this chart. So two examples. ChatGPT is both a model and an inference. So in the case of ChatGPT, it analyzed vast data sets and refines it with human feedback. And then when you're chatting with it, it responds with conversation, with image content, software code, summarizations, language translations, etc. Another example is a self-driving cars. So Waymo has a Waymo World model. It's a 3D model for traffic. And the inference part of Waymo is when the car is running and it's instantly recognizing a stop sign or real time while driving. Another set of terms are apps and agents. So examples of AI apps are a plant identification application or ChatGPT. So in the case of it's a specialized task, the plant ID will just do plant ID. And in the case of chat, it's a chat assistant that you can converse with. So what agents are is it's a entire software system that automates a set of tasks, so which makes them AI workers. So in this case, it's a sales agent. It takes incoming emails, web forms, chats. It analyzes them, tags them, routes them, and then the other end of it, it'll create a CRM record, send an email, and post some social media. In a typical organization in the future, there'll be hundreds, if not thousands, of these AI workers all working together. The HR apps working with the accounting apps, working with the sales apps, et cetera, the marketing apps. And again, we're expecting there'll be 30 billion of these running by the end of this decade. The currency for AI is tokens. So it's a unit of data process, one token for every 75 words. And um, people, the models like ChatGPT, right now they support about 128,000 tokens, and otherwise it'll time out. So some of you that have tried pushing huge jobs into them might find that they just get bogged down. It's because their limit has been set at 128,000 tokens. So the more tokens that software engineers use, the more accurate the model is, but the more costly it is, the more infrastructure it takes. And what we're seeing is that enterprises, organizations are now setting budgets on their tokens. So now they've got lots of users using them. They have to keep an eye on the cost of all these tokens, and they're looking at tokens per user. And on the development side, engineers are carefully monitoring how many tokens it's taking to do, and they're engineering around the usage of tokens. A simple view at AI power consumption. A large data center before AI consumed typically about 100 megawatts, which was equivalent to powering 100,000 homes. We used to think that was incredible. Now, the largest data center sites like Stargate in Texas, 7,000 megawatts, which is equivalent to powering 7 million homes, or the city-state of Singapore. A whole new scale. So now those are some of the basic terms that we need to be familiar with to understand what's happening, starting with the Gen AI Big Bang. So the founder of LinkedIn says AI, like most transformative technologies, grows gradually, then arrives suddenly. It's true, but it's a huge understatement. In a single day, on November 20th, 22, ChatGPT was released, and it just sparked the big bang of generative AI, billions of users, trillions of parameters and models, trillions of dollars invested, amazing intelligence in our AI capability. ChatGPT grew to 1 million users in 5 days, and it'll pass 1 billion users this year. And Gemini, Google Gemini is right behind it. It'll pass 1 billion users next year. So this happened so quickly that it created a short-term spike in the need for power. And what this chart from semi-analysis shows is that in just the 4 years from 23 to 28, there was a 4x need in critical IT power. And their definition of critical IT power is the compute resources, servers, networking, storage, memory inside the data center. And back to inference versus training, this chart shows that inference is going to emerge as the most power hungry part of computing. So in 2025, it was actually the lesser part between non-AI, inference, and training. But by the end of the decade, it's going to be the larger part. And my expectation is that in the following decade, it's going to look like that 80-20, 90-10 model where AI inference is going to dominate the use of the need for power. Um, in terms of in the US, there's 2 points I'd like to make here. One is the need for data center power has grown 3x in this time window. But the other point that you can see here is that although it's grown so explosively, it still is only growing up to 11, almost 12% of total power demand in the US. So what that suggests, and we know is true, is that other industries, their need for power is growing very rapidly as well. So for this one segment that's growing very rapidly, what the data center companies have learned is that the governments and the grids just can't react fast enough. And so what they're doing is they're taking matters into their own hands and securing power on their own. So what we saw in Tennessee is that Tesla or uh, XAI couldn't get Tennessee to move fast enough to get them the power they needed, so they just reached across the border into Mississippi to get the power that they needed. Meta is going to build 10 gas-fired power plants on their own property down in Louisiana, and Microsoft and others are doing deals with the nuclear power plants to secure the power that they need. It's also the same dynamic is changing the power hub landscape. So the states in the red where you found most of the data centers, they're now moving into the green states where there's excess grid capacity, cheaper rural land, or down in the south where they have the bring your own power model. And in both cases, they're getting tax incentives. So just build more data centers and we're okay, right? Well, no, we're not. We need to have efficiency, and I'll tell you why. So here's one estimate that shows that if you combine the compute power and then the need of the power needed by the computation and the power needed by networking, that we're going to run out of power by 2055. The entire planetary human energy production is not enough to satisfy the power that's needed by um, industry and the data center business. So those green lines, what they represent is what the industry is targeting is to have a double even efficiency every 2 years, and that'll get us where we need to be. And what this shows is how it's going to get done. So this represents a blog that was done just a couple of days ago by NVIDIA. And what they're saying is that most people have their eyes on peak chip specifications. Everybody's writing about cost per GPU per hour and how many flops the latest Blackwell chip can execute. But the meaningful work is being done beneath the surface where there's a massive amount of integration being done between the compute resources, the power resources, the facilities, so that we can drive down that efficiency, and that means cost per token and tokens per watt. So to that end, I'll go through the top 6 ways of improving efficiency, starting with liquid cooling. So first of all, cooling consumes 30 to 40% of DC power, and liquid cooling can cut that by 65%. So that's a huge 25 to 40% of the total efficiency gains, and the whole picture can be done simply by implementing liquid cooling. The second is more efficient chips. So what this chart shows is the trajectory of efficiency, power efficiency by the new generations of chips. And the trajectory is 40% per year. So that's pretty good. So if a point of reference is the Frontier supercomputer, which was released as one of the biggest supercomputers in the US, was way below what these new chips can do. However, our new chip technology is still way behind the efficiency of the human brain, which is 5 times 10 to the 16 flops per watt. But if we do the math, we We know that in about 30 years, if we maintain this trajectory, that we'll be as efficient as the human brain, which can do a petaflops of computation with only enough power that it takes to light a light bulb. That's pretty amazing. We'll be there in 30 years. The third way is to eliminate power conversions. So if we can implement DC power, and Shaun's going to drill down on this, then we can eliminate 10 to 25% of, this will achieve 10 to 20% of the total efficiency gains by eliminating all these power conversions, as many power conversions as possible. Number four, AI-driven workload optimization. And this speaks to this integration, managing the data centers from end to end, power, cooling, down to the GPU level in real time. It's all being managed so that it can take advantage of it's energy aware, so it can take advantage of the cheapest energy to do workloads, etc. There's companies like Pato and Vessel that have partnered the cooling vendor with the GPU optimization vendor in order to achieve this. Number five, renewable and alternative energy integration. So what the data center companies portrayed by this image in the middle are doing is they're working to co-locate with solar, wind, hydro in order to reduce grid losses and emissions, alternative sources like small modular reactors, and that energy aware scheduling and workload management that I mentioned on the earlier slide. And number six is all new architectures that can optimize the entire system, not just piece parts, is what we're doing mostly today. And if we can do that, we might be able to squeeze another 10 or 15% out of the total efficiency picture. And the prime example of that is moving data centers into space. And that's being seriously looked at today. So to wrap it up, if we can achieve all those efficiencies, then we should get there, right? Well, maybe not. And that's because of Jevons paradox. So what this picture of the background shows is that the auto industry has learned that if they achieve, the more they achieve energy efficiency with gasoline fuels, is that it just spurs more driving, more cars, and more miles. And we can see that applying to AI. So even though we achieve higher data center efficiency, we expect that to decrease usage need for power, but what's actually happening, it's increasing the usage and the need for power. And one prime example, no pun intended, is Optimus Prime. So this represents a new source, a new need for power. We expect that in the near future, there's going to be millions, if not billions, of these robots, these AI robots, walking the Earth. And they will need tremendous amounts of power because they will have vision, they will have hearing, they will have smell, they will have taste, they will have touch, each supported by massive models for each one of those senses. And a lot of that power may be needed on the edge in your home to charge them. But my expectation is that the need for power is going to continue to grow dramatically for a long time. That's all I have. With that, I'm going to turn it over to Shaun.
Thank you, Frank. All right. So when you think about the move to DC data centers, one of the big questions that is still, I think, lingering for a lot of people is why. So Frank talked about the efficiency, he talked about the capabilities, and what some of the results are. I want to talk as much about the how as the why, because they go together in a cause and effect way that I don't think a lot of folks have spent a lot of time considering. So one of the big milestones for this webcast was at NVIDIA's GTC conference this year. They introduced their DSX architecture and a number of tools for using AI to optimize AI in order to have AI data centers, which again, may be a bit of circular logic, which today also seems to be the financing model for most of the AI industry as well. But I wanted to kind of drill into that because it is the core capability that gives you the how. Without the standards, without the ability of everyone else to look at this, without the ability of everyone else to implement this, it's just another piece of paper. So we're going to talk about how do we take it from being a piece of paper to being an operational reality. All right. So let's talk a little bit about what's driving the challenge. So as Frank said, when we talk about the scale, one of the things AI or AC based data centers have always had a degree of inefficiency to them, just like conventional industrial combustion engines are less efficient than EV engines. That's simple math. But it doesn't change the fact that we still sell a lot more internal combustion engines than we do EVs. And that's kind of been the case with DC data centers for the last 50 years. And as Frank said, even as we scaled up in the cloud, it still wasn't quite painful enough. AI is making it painful enough. So let's talk about what's happening. So starting with the grid itself. So once you take energy off the grid, you're losing efficiency in terms of the step downs. You're going from high voltage to moderate voltage to go into the data center to very modest 110, 120 voltage to the individual devices. Then you need to make sure this is available on a 24/7 basis, which means everything has to have battery backup, everything has to have system backup. And what we're discovering is that in a lot of these cases, batteries aren't the most efficient way. And we'll talk a little bit more about that as we go in. But then you lose another 3 to 5% of the power going into these. And again, this continues to go through each step where you're losing power efficiency because you're either converting from AC to DC or you're transferring power over longer lengths of cables. And then ultimately, when you get down into the racks and you're getting down to the actual devices, you're moving at 48 volt or 12 volt DC, sometimes 5 volt, and even down to 3.5, depending upon the individual chip level. And every single one of these transitions sucks power out of the efficiency. And this kind of goes back to what Frank was saying about the paradox that we're trying to solve. So as we look at what's happening right now, when you think about the trillions of dollars that have been allocated for this across power grid, across data centers, across the infrastructure going into those data centers, if 15 cents on every dollar is lost, so $150 billion is currently wasted by continuing with AC. This is why people are doing this. So this is just the first of the major economic dollar reasons why. So how do we take $150 billion of loss and get that down to, let's say, $10 billion? Because that's all either direct profit, new capital that can be put in there, and continue to go through the rest of the infrastructure to decide where you want to reuse those dollars. Oops, sorry, one too many. All right. So what are the places where you can fix it? So number one, we can't fix the grid. Sorry, guys, it is what it is. But what we can do is saying now, once you put it inside, you're going to lose a little more up front, but now you start to get a lot more efficiency. Okay. So what do? The biggest thing is you get rid of the UPS and you go to a standardized 800 volt busway. This is the infrastructure operational change that starts to save a lot of the money. And because you're starting with DC coming right off the grid, while you pay a little bit up front, you're going to save a lot more in the back end. And it goes down to box 6, the efficiency of how much power you get to the servers and the GPUs in the system. So as we're going through this, these are the numbers you want to pay attention to on the back end, because this is what drives the scale. So about a 12% improvement between an AC data center and a DC data center. Again, you're spending $1 trillion a year. That's $120 billion of efficiency that we can bring back to the system. So what's changing in this? So there's three ways in which this is changing the architecture. Number one, eliminating parts, fewer transfers. Second is moving to solid state, which is significantly more efficient than the analog transformers, switches, and other things that have been used. And then the third part is the data center racks run natively on DC. So we're giving them the native power that they need. The other big thing that changes in this, copper. Think about the price of copper these days. Think about all the struggles in getting that type of material. We cut the need for copper almost in half by going to DC versus AC. This means that you can put more equipment that generates revenue on the back end of DC data centers. So your operating cost is less, your material cost is less, and the output scales because you can run more GPUs off the same system. So we think about how that efficiency scales. So depending upon how you want to look at this, you can say net 5% end-to-end, which is, pretty modest. But when you look at maintenance costs, you've taken out a bunch of systems. That drops dramatically. Total cost of ownership drops because, again, far fewer parts, fewer things to maintain. Your copper drops. But look at this last one, GPUs per megawatt. You're increasing by almost 40% how many GPUs you can run off the exact same power into the data center. And this is the real magic behind why this architectural change is so significant, why it changes the game. And it helps alleviate some of the power generation issues we have, some of the grid limitations we have in terms of getting the power from the generation source in. And this addresses some of the scale parts. Just with this architectural change, 40% more AI capability and cloud capability. So this is, again, it's not just hey, it's more efficient or it's better for green energy and all those other things. It has material, measurable revenue growth, and it helps address the bottlenecks that we need years to recover from. The CEO of GE Verona in his last earnings call, who is basically the largest producer of natural gas power plants in the world, said they are sold out through 2030. They don't have the factories to build enough new gas power plants. What we have is what we're getting for the next 4 years. So if we change and get smarter about how we implement all of those thousands of new data centers by using DC, we help bridge that gap over the next 5 years that it takes to move all the infrastructure shift that we need. So this is one of the other critical reasons for why this DC approach is getting adopted so quickly with new data centers. So what changes inside? Obviously, you change the bus architecture inside the system. You go to this 800-volt busway. This protects the equipment. It protects against power issues. It protects against outages. You change the distribution system inside how the power is moved. You change the rack usage. And this is what starts to give you the real scale to grow the number of GPUs per megawatt into the system. And the other operational part of this is shifting from batteries to supercaps and to other types of DC based capacitor systems in here. So this is a fundamental architectural change inside of it. I would love to claim that it is only because of our wonderful nanoplex capacitor film that the world is doing this, but we're more of a beneficiary of great serendipity. Turning on the Wayback Machine, Frank and I used to work for a company called Quantum. The CEO there once bought a hard disk drive company, and they said, "Oh, you got to take the tape business, or else we won't sell you that because we don't want the tape business, but we need someone to maintain the customer base." A year later, we had shut down the hard drive business, and we're doing $1 billion in tape. So as Mike Brown, the CEO at the time, said, sometimes it's better to be lucky than right. This is one of our lucky versus right moments. So what does that mean in terms of what data center growth and capacitor markets are going to be. This is, if everything that we've seen from the predictions are right, of the new data centers built between now and 2035, we're going to see almost 80% of them switch to DC. It just makes so many economic benefits. That in turn is going to drive some of the capacitor business that we're talking about. But it's the fact that you have the GPU guys, the power grid guys, you've got the memory people, you have the people who build the infrastructure, you have the people who are building the data centers who are looking for, if I put, if I make this investment, how do I maximize my return? This is a hardcore economic and scaling benefit that is driving this behavior in the market. So the biggest problem that people have across this is also synchronizing the workloads, because this is driven by power, this is driven by consistency, this is driven by how efficient the power is delivered, and how are all of those GPUs, inference instances, memory, storage, in-memory databases, all of that, how are they running together? They need fast cycle times. And that is one of the things that capacitors can deliver that batteries can't. They're designed to have much higher cycle times, and this is what helps drive the efficiency of the entire GPU architecture. You can see here from the specifications that the amount of growth in the joules of energy, this requires faster energy storage. And think about this a lot like a Tesla. If you're running a Tesla straight off the battery, what happens? You get a constant feed of energy off a battery. But if you're backing out of your driveway, you want just a little bit of energy. That's where capacitors come in, is capacitors regulate that difference between the DC power coming off the battery or the DC power coming off the 800-volt busway into the system. But if you put your Tesla in ludicrous mode because you want to embarrass the guy with the Porsche turbo next to you at the stoplight, that needs a whole bunch of power dumped all at once. And that is also what capacitors do. So it's this ability to control energy, to drive scale, to drive reaction to surges in compute, inference, memory, storage in the data center for why this architecture is happening. And then from there, it's just the sheer cost benefit to all of this versus batteries. Capacitors cost 10% of what batteries do. So again, this is another one of those operational efficiency things that you gain out of it. Doesn't mean that you won't have backup systems, doesn't mean you won't have UPS systems, but their responsibility is changed in the DC data center. So this is where all the different capacitors live inside the data center. And I am certainly not going to attempt to read all this to you. But what we want to emphasize here is the architectural change, that when you go from AC to DC, the entire infrastructure changes. So this isn't just a walk up to an existing data center and rip it out. You got to start from scratch. And this is one of the biggest changes. And this is why NVIDIA said, we are going to publish the definitive standard. And then Siemens and Eaton and Schneider and GE and Vertiv and CoreWeave and all the people doing the data center side, they lined up behind this. And this is what's going to happen, because these are the people that buy the real estate, build the buildings, build the infrastructure, and turn them on. Satya Nadella from Microsoft said, today, I have over 500,000 NVIDIA GPUs sitting in a warehouse. I have shells of data centers built, but I can't turn them on because I don't have enough power. Every time he turns on one of those data centers, we can turn on another half of a data center with just the efficiency of switching to DC versus AC. That's the type of operational power that this thing has in the market. So what does that mean in terms of why they're doing this? Well, all right, we talked about energy density, that sort of thing. The other thing is these things run hotter. DC, because of the high cycle rates, more friction, you're moving to silicon carbide or GaN-based controllers, that's going to raise the temperature. The old AC stuff literally will melt. We didn't do video on this because it's a little hard to show. It doesn't always go fast over Zoom, but the previous technology, the electronic systems just aren't built for it, and they will literally melt in place. So one of the other things that reasons you have to do this upgrade is to deal with the temperature issues. So what are we trying to do here? Biggest thing, I'm going to actually start on the right-hand side here, burst of power. You got to have big surges of power. You got to be able to control them, and you need to be able to match them to the battery infrastructure, to the DC link infrastructure, and to how the power is absorbed. Once you give that burst of energy across the main DC busway, once you get it inside the rack, it needs to be smooth. It needs to be perfectly delivered. It needs to be 100% synchronized with the controllers inside that system. So there's a two-tier architecture here. The Nanoplex HDC capacitors that move big energy, and then the Nanoplex ones that deliver it perfectly and precisely at exactly the right moment. And the other big benefit to these new technologies, 10 to 15-year life cycles versus 4 to 5-year life cycles for the previous. So again, this is why that maintenance cost goes down over time. And this technology is all built, manufactured, and delivered in the US or allied nations. Today, on the AC side, 80% of those materials, the transformers, the switches, the rack infrastructures, all come from China. So this also helps us build a stronger, independent infrastructure that we need as we compete in the market. So getting down to the big money slides. If you want to run 4,300 GPUs per megawatt of power you put in there today, you're going to lose 14% of that. With moving to DC, you're going to pick up about 12%. When you move to the new AI simulator that NVIDIA has put out, and then you move into their architecture, now on the same megawatt of power, you go from 4,300 GPUs to 6,100. 42% increase in the amount of compute and billable operations that come out of each data center. This is why this is going to happen. It is a pure dollars and cents play. This is not a technology looking for a solution. This is a market that needs to scale and needs a new way to do it, and we help them deliver that. So as I am fond of saying, those are the end of the prepared remarks. So with that, Jalen, hopefully we have some questions.
Yes, absolutely. So as we are going into this Q&A portion, we do have a poll that should be popping up on your screen shortly. If you don't mind just taking a second and going ahead and starting with that. While everyone is getting started on that, I will ask the first question. So as data centers are moving towards the south and other regional areas, there seems to be a pushback against these data centers. Do you think that all of these data centers will be allowed to be made?
Frank, you want to take a first crack at that one? You're on mute, Frank.
Yeah, sorry, I'm getting my controls here. Number one?
No, the question on the data center pushback that we're starting to see in some communities, we want to build lots of them, and I don't know about you, but I'm certainly seeing the beginnings of pushback. There's regulatory stuff that's, people are starting to try and ban data centers and that sort of thing. So how do we balance that difference between the demand and the impact on communities?
I guess my answer is maybe it doesn't answer the question, but what I see is citizens and politicians have different views of it, and it's analogous to I'm a Chicago Bears fan, and the politicians want to fund the new stadium in Illinois, but the citizens don't want to pay for it. The citizens don't want the data centers in their neighborhood, and they don't want the noise, and they don't want the data centers to take all the power and raise their rates. And so that's the dilemma. I mean, if somehow the industry could actually build more power, improve the grid, and it turns out to be better for the citizens, then I think everybody's happy.
Yeah, I think when a lot of people look at data centers today, there are three big challenges. Obviously, is the power consumption. So depending upon where you're going, power companies have a choice. They can sell energy at a higher profit to the data center folks because Google, Meta, and so forth can afford it. Unfortunately, that means that they end up charging their consumers far more, and that is one of the big rubs. Jalen, coming from deep in the heart of Texas, understands there's not a lot of water. And most people don't think of water as a key part of deploying data centers, but it is arguably the biggest problem with deploying data centers and the impact on communities, especially since a lot of these data centers tend to go into semi-rural areas and impact farming and livestock and other sorts of things. So they face an uphill battle related to that as they go forward. The third big problem is they don't bring a ton of jobs. This is not like building an auto factory or a battery factory or some other factory where they're employing a lot of people. These tend to be almost like black sites. They put them in, they suck up resources, they take money out, but don't necessarily give a whole lot back. And I think that's one of the other big issues that they have. And to Frank's point earlier about the hyperscalers becoming power companies, this is what's driving it. President Trump had a new executive order saying that if you want to build data centers, you have to provide, I think it's 75% of the new power demand directly generated by that company. Now, if you're Meta or Google or Microsoft, you have the option of helping the local utility build out that infrastructure, which is a lot of what Google has done in Texas. If you look at the XAI facility, they've opted for buying 600 acres and putting their own solar farms in as one way to do it. Microsoft is working with Helion Energy to build one of the first fusion power plants in I forget the name of the town in Washington, but it's towards Spokane. So each of them are solving it in different ways. So one of the other data points that Frank put on the slide was a joint venture between Constellation Energy and Microsoft, ironically, to open the notorious 3 Mile Island nuclear power plant that melted down in the 70s to power their data centers. You can either say desperation or necessity is proving a great deal of new invention when it comes to ways to power these data centers. And I'll leave you with one last data point, which was a comment from Jensen Huang, the CEO of NVIDIA, which was, if China wins, it won't be because they have better chips. It'll be because they have more power available to apply to chips. Because the scale of flops that they can create, even if it's with inferior technology, is arguably the single greatest risk the US has in maintaining AI leadership. And make no mistake, our leadership is hanging on by a very, very thin thread right now. So that is a very long-winded answer to what the politicians want versus what the communities want. But it is a very, very real dynamic that if we don't solve it, in many ways could hinder the growth of AI and the way that not wanting power plants and other sorts of things, prisons and other things, what's the expression, Frank? NIMBY, not in my backyard. There's a lot of that going on right now with data centers. All right, Jalen.
All right, our next question is, Your timeline shows Kyber Rex shipping in 2027, making 800 VDC mandatory, but most hyperscalers have 10 to 15-year leases on existing AC facilities. What's the realistic adoption curve when installed base is overwhelmingly AC?
So I think that's a question of phasing. If you look at Google today, Google Ads, which is their most profitable business on the planet, is not necessarily always served by AI. A lot of that is done with existing cloud data structure. If you're going to store your latest photos or videos, or you're using iCloud or other things on the back end, the vast majority of the cloud is still going to use AC data centers, and it's a question of where they shift the workloads. The new workloads are the ones that are moving to this DC data center. And for all the scale that AI has and all the other work that's being done, when you compare that to the amount of data generated on a daily basis off of mobile phones, off of files, off of basic e-commerce web transactions, that all exists and will continue to grow in addition to the AI parts of the market growing. It's just a question of the rate of growth and the exponential addition that AI brings. So I don't think it's an either or. It's a shift of workload and cloud plus AI.
Awesome. And then we have time for just one more question. So this last one is going to be, you claim that NVIDIA specifies capacitors over batteries for rack energy storage, but the Vera Rubin spec sheet mentions energy storage generically. Where is the explicit NVIDIA specification that says film capacitors and not batteries?
So it has to do with the change in the architecture inside the rack. So if you, on one of the slides, and you'll be able to see it, we call out both power supply for backup. So that's the best reference, the battery enhanced storage. And then there's also storage inside the rack, and they're different purposes. So the backup power supply, and what you traditionally would get from Frank, who bought APC? I forget. One of the big power companies bought APC.
I don't remember.
But it's the traditional battery backup system in racks. That's going to move out of racks and into a centralized area that'll look more like a solar battery storage area that is shared across the systems. Then there will be capacitors inside each rack that give it the higher bandwidth usage and synchronization. Because when power does fail, and Frank spent a lot of time in this in the cloud area, if you have to snapshot your memory or snapshot everything in your Kubernetes environment or anything that you want to have stateful restore on, you need very, very fast power transfer, or the memory will lose everything. And that's where the high performance of the capacitor, the high switching rate, and the ability to synchronize the power demand is very, very different than the traditional battery backup. So it's a question of where those power sources live in the architecture, not that one eliminates the other. One complements the other based on different application requirements.
All right, so that's going to conclude our Race to Win AI webcast for today. If there was any questions that have not been answered, we will reach out to you directly with those answers. So thank you to all of our viewers for joining us today, and a special thank you to both Shaun Walsh and Frank Berry for their insights into the next generation of AI and data centers. If you are interested in joining us again, please pay attention to your inbox where you will receive the slides from today, collateral around our discussion, and information about our next webinar, Films as a Service, Overcoming the Rule of Mixtures with Nano-Layered Films. If you have any topics that you would like to see, or if you would like to be a panelist, please reach out to whatsnext@peaknano.com. So thank you again for attending, and please stay connected through the following platforms.